and you've looked at your bonding unit, you've probably looked at what intra and intermolecular forces are. So I just wanted to go over it because I was helping a student earlier, and this was coming up in Chem 30, and we had to go over all of this just to help with that concept. So you do learn this in Chemistry 20, but the theory comes up over and over again, including when you're in university. So to start off with, just knowing that there are different forces present and what's strongest to weakest. So I just started here to kind of making a flow chart. So your intramolecular forces are the strongest. So between ionic and covalent, ionic is stronger than covalent. And then you have your intermolecular forces that only apply to covalent bonds. And as you move down this list, they get weaker. So if I made this kind of like a little line, this would be your weakest type of force, your LDF. And as you go up this, it gets stronger. So in terms of forces. And then this last point, the more intermolecular forces that are present, the stronger your molecule will be. So if you had all three of these forces, you are a very strong covalent bond. So looking at intramolecular forces, this is within the molecule. So if you took a look at how sodium and chlorine come together to bond, right, how they form this bond is that attraction between the positive and negative ions, and that attraction, this bond, is an intramolecular force. If we looked at something like methane, so CH4, same idea, the covalent bond are the bonds that are holding those atoms together, so within the molecule. Intermolecular forces are the forces that hold molecules together. So when we're looking at intermolecular forces, we don't have to look at ionic because they just have that ionic bond. But what we do look at is our molecular ones and to see which one of these are present. So when we are looking at that and which ones are present, we start with LDF forces. LDF forces are going to be in all your molecules. So if you think of just like even looking at that CH4 one more time, it's going to be what attracts this to itself, right? So the bond that keeps these together, that's an intermolecular force. And again, every one of our covalent bonds have LDF forces. If this last other part here, if you only have LDF forces, how do we know which one is stronger? So if we're comparing molecules, which we will in an example, and you only have LDF forces available, then the next thing you look at is your number of electrons, because that will also determine how strong your bond is. And the more you have, the stronger it will be. Now, the next force is dipole-dipole. When you looked at your bonding unit, you want to see if there's a dipole present in your molecule. And if there is, then it has a dipole-dipole force. So for instance, you have comparing CH4 and CH3Cl. CH4 is a symmetrical molecule. Even if we filled in some electronegativities, we would see that all of our dipoles point inside and they would cancel. So this is not a polar molecule, but if we drew out CH3 and then had one thing different on the outside, like chlorine, then we now have a dipole, because as we take a look at our molecule, we have our hydrogens will lose its electrons to carbon, and same thing over here, but all carbons, it will be losing, in a sense, their electrons to chlorine. So this gives your overall molecular dipole going from left to right. And both of these molecules would have LDF forces, but this one now would be the stronger one because they also have dipole-dipole forces present. Now, the last one that we're looking at is hydrogen bonding. And if you are having this force present, you have a molecule that's directly bonded to a nitrogen, oxygen, or fluorine. So for instance, we have, hydrogen has to be directly bonded to this. I should have that in there. So for instance, water, if we drew this out, we know it has that bent shape. We know that there are some valence electrons hanging out there, lone pairs, and we have that bent shape. Now, there's not hydrogen bonding directly within this molecule. Where the hydrogen bonding is if we drew another molecule out, and you also still have those, lone pairs, you would have this end being slightly positive, this end being slightly negative, and this attraction is what makes our hydrogen bond. So the bonding between the oxygen atom and the hydrogen between those molecules, right? Because inter is always going to be between. So that's what we're looking for. One thing that I emphasize is something, again, like CH4. Just because you have hydrogen present does not mean you have hydrogen bonding. You must directly be bonded to oxygen, nitrogen, or fluorine. So this is part of an activity that I used to give in Chem 20. And this is just comparing between the two molecules, which one would have the higher boiling point. So starting off with number of electrons, sulfur has 16, oxygen has 8, but there's 3 of them. So then that's a total of 40. S2O2, doing the same thing, just adding them all up, that's a total of 48. Now looking at forces, always with molecular compounds, so I'm just going to keep going, you have LDF forces present. Now dipole, you want to see if your molecule has a dipole overall within. So if I looked at the SO3 molecule and started placing, I end up with this shape, and I do get a double bond in there, but because of this symmetrical shape, and this is an AX3 shape, this has no overall dipole. So we don't have this, and even though we have oxygen present, we don't have hydrogen directly bonded to it, so it also does not have hydrogen bonding, and that's going to be true for the second one as well. Now, if you draw out S2O2, it has a more interesting shape where you end up getting a bent shape around each of your sulfur atoms, and then you have oxygen on the end, and then you have these lone pairs that still end up, I'm not drawing this exactly right, but you still have these lone pairs that cause that bent shape. And I believe you ended up with a couple double bonds as well to make this work. But anyway, the bent shape is what matters. Because you have that bent shape around the sulfur, you do have some negative ends, which will give you an overall dipole. So you do have a dipole present. So now comparing between the two, the one with the higher boiling point would be the one with more forces present. So that will be your S2O2. Looking at our next one, again, adding up your electrons. Here you have 10 electrons, and then the second you have 18. Now, both of these molecules are linear, but there is a difference in electronegativity, right? Hydrogen is 2.2, fluorine is 4.0, so electrons want to tend towards fluorine. When you look at the same idea with chlorine, they want to tend towards chlorine. So it definitely has dipoles present. And then in terms of hydrogen bonding, again, you have to directly be bonded to nitrogen, oxygen, or fluorine. So the chlorine one does not have hydrogen bonding, but HF does. So just with that alone, the one with the higher boiling point would be HF because it has more forces. Now, just one more thing to mention here. If your forces are all exactly the same, then look at electrons. So if by chance, say this one, we didn't have a dipole and we just had LDF, then the stronger force or higher boiling point would be the one with more electrons. So first look at forces, which one has more forces present, and then start looking at electrons if they're the same. So just going on that, this concept will come up further in Chemistry 30, where it appears definitely is in organic chem, especially looking at comparing boiling points of organic compounds. So for instance, because an alcohol has hydrogen bonding, that would mean it also has a dipole, it has LDF. It is going to have a higher boiling point than a simple alkane. So things like that are going to come up in terms of theory. So just being aware of that and what affects your boiling point in terms of those dipoles and hydrogen bonding. As always, I hope you found this helpful. If you did, please subscribe. If there's any other video I can do for you, just leave me a comment, and I will continue with some more calculus videos and chemistry videos. And again, I would love some ideas. Thank you for watching.